Good evening, everyone. I welcome back to the webinar series on quantum algorithms using Qniverse. Last week, Mr. Jotishwaran helped us gain a clear understanding on Shaw's algorithm, how it is effectful in breaking the cryptography, and he also made us understand on the cryptographic part. Uh, I hope all the participants refreshed their learning and answered the quiz questions which we had posted on our channels. Before we move on to today's session, the session materials will be available on our GitHub channels. You can have a look, and we also have a WhatsApp public channel, so you can join to that. We will keep sending the notifications in that channel also. Uh, Keep the chat clean, or ask only the questions to the speaker regarding the subject so that he can answer your questions. And today's session is on Bernstein-Vazirani algorithm, which is a fundamental quantum algorithm that demonstrates the power of computation over classical computation methods. So again, this week we have with us Mr. Jotishwaran, who is a PhD scholar from IIT Roorkee. He is pursuing his PhD at IIT Roorkee with a bachelor's degree in electrical engineering from IIT Jodhpur and a master's degree in physics from IIT Roorkee. He has delivered many lectures past in several courses and online sessions in quantum computing. Even CDAC also had conducted earlier some of the courses, and he had gracefully accepted the invitation and conducted. Thank you, Mr. Jotishwaran, for accepting our invitation in delivering these two important algorithms. One is on Shor's and one is on the Bernstein-Vazirani algorithm in this webinar series. Over to you, Jotishwaran.
Okay,
Yeah.
so let me not waste any further time. Let me quickly share my screen.
Okay.
So yes, can you confirm that my screen is visible?
Yes,
Thank
please
you
go
very
ahead.
much. Yeah, let me also open the chat so that I can keep track of things. So I'll also move this over here. And yeah, that should do. So yes, today, as was mentioned before, I shall be covering the Bernstein-Vazirani algorithm. And as it was correctly mentioned, yes, this algorithm was the first to prove several major separations in the complexity between classical algorithms, classical computing, and quantum computing. They were able to show that there exist at least certain class of problems that will have a definite speedup when run on a quantum computer as compared to a classical computer. So we shall be studying, like, essentially we'll spend some time defining the problem. As you will see, the problem is not something very deep, or I mean, it is a deep problem, but it is not something very complicated. It's a fairly straightforward problem. And the solution to the problem also comes from, as we saw before, a very definite classical mathematical theory. So, but before I begin the session, there was actually one question from the last presentation that I did not answer. It was a very basic question. So people were asking about reading materials. So let me quickly make a note of that over here so that when I share this, you will have access to all the things. So for quantum computing, well, this is both a good thing and a bad thing. I have been like studying quantum computing for what 15 years now.
So that's
So
great.
yeah, so
That's a long journey.
unfortunately, yeah, I still refer to the old books. I don't refer to the modern. In fact, I don't even know how many modern textbooks are out. So for quantum computing, I will give the standard references. So quantum computing, which is algorithms, quantum error correction, QKD, and all those things. So we have the first one is, quantum information and computation, or the other way around.
Maybe it would be better if you type it instead of write.
It's, I mean, I like, I need to, move here and there. It feels a bit, I will, quickly finish this off.
Okay.
Wait, yeah, and computation. So this is Nielsen and Schwann. So this is a famous book now. So you can look this up. But this is also a very exhaustive book. It covers a lot of the mathematics that is required. It goes into the depths of it. So there are very nice discussions. If you want a slightly easier read, there is this book called Quantum Computing. A gentle introduction. So this is a gentle introduction. So this is by Riefel and Pollack. So this book came out like, I think, almost 10 years ago. So this is by Riefel and Pollack. So these are the two books that I usually follow. And regarding last week's subject, like classical cryptography, where I was talking about Shores and all the other crypto systems. So for that, uh, crypto. So there is, I do not remember the title of the name because we rarely refer to the book by the title. It is the book by Douglas Stinson. So just type cryptography and Douglas Stinson, you will find the book. I think the latest edition is the fourth edition. So that is where all the theory for RSA and all the things I used. So these are the reading materials. So now, without any further delay, I'll begin the session. So first, again, a glossary. These are things that we already know, but nonetheless, we shall,
Good to
uh,
refresh.
yes, it's good to have a refresher. So a bit, which is short for a binary digit, is a number that takes two values, 0 and 1. A bit of an unknown value is also known as a Boolean variable. Additionally, this bit also refers to the most fundamental unit of classical information. This is a context that is usually applied only in information theory, or mostly in, I should not say only in, mostly in information theory. So we will not be using that here yet. Maybe if we were doing something like QKD, we will be talking about the information theoretic aspect of this, but we are not going to do that now. A Boolean function is a function of one or many Boolean variables like bits. So these are constructed using classic logical gates. So your AND or NOT gates, or NAND, XORs, and stuff like that. And then we are talking about measurement. We'll briefly talk about measurement in today's session. We'll not be spending too much time on it. So one thing we should remember is measurements are the only known method to extract information from a quantum bit, from a qubit. I'm not defining what a qubit is once again because, for obvious reasons, we should be knowing that well enough by now. So the only way to extract any kind of measurement from a quantum bit is by measuring it. When I measure a single quantum bit, I will get one classical bit's worth of information. That is that. And the measurement is also known as observation. Okay, so yes. Now, linear systems. Today we shall start our discussion with linear systems. So when we talk about a linear system, typically whatever it is, ultimately it can be reduced to this form. I can write it as a dot x equal to b. Dot is an appropriately defined kind of multiplication. So whenever I'm performing multiplication here, I will be using the dots, but each of these dots may have a different definition. So I'll quickly put that up over here. So dot is multiplication. And this is context dependent. So If I'm multiplying two numbers, I'll use the dot and it implies like standard numerical multiplication. If I'm multiplying two bits, it is the multiplication of bits. If I'm multiplying a matrix and a vector, it is the corresponding matrix multiplication. So all of that is understood. Like I'm not going into the details of it. So please follow that. If you have any doubts, feel free to depend. Yes. Okay. So here x and b are vectors. Typically in a linear system, x is the unknown. And a is an operator defined over the vector space that contains both x and b. So for the above system to have a unique solution, now this is like high school mathematics. So I assume all of us know what's going on here. So, oh, sorry. For this system to have a unique solution, whatever, like now I'm assuming that, you know, these vectors are, let me say, finite dimensional. These vectors are finite dimensional. Just for simplicity's sake, but whatever I'm saying here is true for any generic vector space. So finite dimensions. So in that case, I can definitely write this matrix as a 2D array of numbers, and there will be rows and columns. The condition that the above defined system has a unique solution is either the rows of A are all linearly independent. So this is one condition. An alternate way of saying this is the matrix must be of full rank. Essentially, this statement is the definition of full rank. Or alternatively, I can say A is invertible. So again, these are things we know. So the standard traditional way to solve this system. So this is solved using the Gauss-Jordan elimination. So that is the algorithm that we use here. There are faster techniques depending on the kind of linear system we define, but the standard method that can solve all kinds of linear systems is the Gauss-Jordan elimination. So if I define a1, a2 till an, so n is the dimension of the vector to be the rows of this matrix, then the vector b can be seen to be this. It is a1 dot x, a2 dot x, an minus 1 dot x, and like all the way till a3 dot x, all the way till an dot x. Here the dot is the vectorial dot product. So it is essentially, if I do all of this, I'm performing the matrix multiplication, but here I'm breaking it down. So what am I doing? I'm calculating a1 dot x, I'm calculating a2 dot x, I'm calculating a3 dot x, all the way till an dot x. If all the a's, a1 through an, are linearly independent, then I can invert this system and find out what x is. And these linear systems are all directly related to an appropriately defined linear function. So ultimately, if I'm saying I have a linear system, then at some level, I can define a linear function that describes the linear system. So if I have a system of linear equations, then there is a corresponding linear function. So I'll talk more about this later. So now we have a binary linear system. Now what is a binary linear system? It is a linear system where the vectors and the operator are defined over GF2 or binary numbers. This thing GF2 here refers to the, so this has a technical name. I'm just mentioning it here. You need not think too much about it. This is the Galois field of order 2. So that is what GF stands for. Alternatively, what it means, these are binary numbers. These are the bits, where addition and multiplication are defined as follows. So how do I add and multiply bits? The answer is like the complete relations are given here. 0 plus 0 is equal to 1 plus 1, which is equal to 0. 0 plus 1 equal to 1 plus 0 equal to 1. 0 into 0 is equal to 1 into 0 is equal to 0 into 1, which is equal to 0, and 1 into 1 is equal to 1. So you can quickly identify that addition. From this, you can say addition is interchangeable with the XOR gate. If we are talking in the terms of bits and logic gates. So binary addition is the XOR gate, and multiply is equivalent to the AND gate. So whenever we have binary vectors and binary matrices and we are performing the multiplication, the most fundamental addition and multiplication are defined using the XOR gate and the AND gate. Now, in this case, like as I told before, every linear system has a direct connection to some kind of an appropriately defined linear function. So in this case, what kind of the function it is? It is defined over, like essentially it has a direct connection to linear functions defined over binary vectors. So such functions are called linear Boolean functions. So associated with every linear system, there is a linear function. If it is a binary linear system, there is an associated linear Boolean function. So what is the linear Boolean function? The linear Boolean function is defined as f of x is equal to s dot x. Here again, the dot is the vector dot product. So what I do is, so here I will essentially write this. I will quickly take. So these are both n-bit vectors. They belong to 0, 1 to the power n. So if I say s is equal to s1, s2, all the way to less n, and if I say x is x1, x2, all the way to xn, then s dot x is equal to s1, x1 plus s2, x2 plus all the way till sn, xn. Here x is the unknown, so this is the like input to the function. I shouldn't call it the unknown. So this is the input, and this is what I shall call the coefficient. Essentially, I am multiplying this coefficient to this linear vector. Okay, so this is the coefficient. So what was the linear function in the case of our general system? The linear function in this case is, yeah, I deliberately did not define it. So the linear function in this case is f of x is equal to a dot x. Again, this can be any vector field. Okay. Up until now, we have done nothing complicated. All of this is grade school mathematics. Like, by class 10, are all the S elements multiplied to get the final S vector? No, 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 no. This is a vector. A vector is just S coordinates. So this is a vector, you can think it computer science terms. This is like a 1D array. These are just, coordinates in a bracket, like that is their structure. So this is, S1, S2, S3, S4. So there are n elements strung together. Yes, I'm doing vectorial dot product, like as I mentioned before. Okay, so, but the vectorial dot product itself breaks down to scalar multiplication and scalar addition, where scalar multiplication and scalar addition have been defined above. Okay, all right. So now again, the rules are the same for all linear systems. For this system to be invertible, I will need n linearly independent values of the function. If I know that, I can find the value of s. So here x can vary. S is an unknown constant. If that is the case, then if I have n linearly independent values of x, I can evaluate it, set up a system of equations, solve it using Gauss elimination and find out s. So it is as simple as that. And yeah, one thing I need to write here. So Gauss-Jordan elimination has a complexity of, so this has a complexity of order n. Essentially, the complexity of this algorithm is just proportional to the number of variables, the dimensionality of the vector space. This is a linear time complexity algorithm. I hope most of you have, implemented their own version of Gauss-Jordan elimination at some point or the other. If not, it's fine. But if you implement it, you will see that it's fairly straightforward. Like this is one of the more fundamental algorithms in mathematics and computer science, truth be told. Okay, so now we come to the Bernstein-Vazirani problem. Now, why did I talk, for the last 10 minutes about linear systems and so on and so forth? The Bernstein-Vazirani problem is stated as given below. Given oracle access to an unknown linear Boolean function. So what do I mean by unknown here? So when I say unknown, I mean that S is unknown. Okay. Remember, X were the inputs. Like X can be any of the possible vectors. S is the unknown vector, which is a constant, which does not vary. So an unknown linear Boolean function, how easily can one find this secret linear coefficient S of the Boolean function? So that is the Bernstein-Vazirani problem. However, this definition of the problem, this is to be remembered, this is not a decision problem. So what are decision problems? Decision problems are problems with a yes or no answer. I'll ask a question, it will tell me yes or no. That is it. It only gives me, in one sense, it only gives me a single bit output. It tells me if the condition, whatever is there, is satisfied or not. So this version of the Bernstein-Vazirani problem, this is not a decision problem. And mostly when we write this complexity and stuff like that, this is only well defined for decision problems. Like, yes, I can technically say, yes, I need order n operations to solve Gauss-Jordan elimination. But the notion of, like, the complexity theoretic notion of, order n or omega n and, big O, small o notations and all of this is truly well defined for decision problems, because that is where we have the idea of comparison. Like to arrive at the same decision, there are two algorithms. So I will compare their complexities. The one that has a lower complexity allows me to arrive at the decision faster. That is like asymptotically as n keeps increasing. Okay, so this version of the problem is not a decision problem. So the Bernstein-Vazirani algorithm offers a constant time quantum algorithm to solve the above problem. So essentially, when I mean constant time, this is, I'll use blue itself. So when I say constant time, I mean the algorithm has complexity order 1. Regardless of the input size, I will be able to give the output in the same amount of time. If I increase the size of the input, now you may ask, what is the input? We'll come to that in a minute. And that is where, so since you've heard me talk about things before, I'm not a super optimist. Whenever I talk about something, I will talk about what are the good things, and I will also try to spend an equal amount of time with the problems of the same, problems in the same formalism or in the same system. So this constant time and size of the input and stuff like these are where, we will run into practical issues. So I hope to spend like 15 to 20 minutes on that. Let us see how it goes. Okay. Now, additionally, there is a decision problem variant of the same problem. So they managed to scale up and turn this problem into a decision problem. And they showed that, again, there is a Bernstein-Vazirani algorithm over there, so which is essentially the same algorithm with some minor tweaks. And they showed that it achieves what is called a super polynomial speedup. Essentially, the if the classical algorithm has a certain complexity, then the speedup factor for the quantum algorithm was greater than a polynomial factor. So again, we'll talk about this when we come to it. So now the rest of the Bernstein-Vazirani algorithm, rather than discuss in theory, it is best to work it out. So let us consider this linear Boolean functions in 0, 1 to the power 2. So we are talking about 2-bit functions. 2-bit functions. So what are the input values? What are the possible input values for 2-bit vectors? So my x is given by, you know what, I will use the computer science notation, x0, x1. So the possible values of the input vectors are 0, 0, 0, 1, 1, 0, and 1, 1. Right? Now, what is a linear function over here? So a linear function f or f of x is equal to some s dot x, where I know s belongs to the same space, 0, 1 to the power 2. So which implies s can also have only these 4 values, 0, 0, 0, 1, 1, 0, and 1, 1. S can also have only these 4 values. Okay. So what are the possible linear functions I can generate with just 2 variables? So they are, so s dot x can be equal to 0, 0 dot x or 0, 1 dot x or 1, 0 dot x or 1, 1 dot x. In this case, the function is going to be 0 dot x0 plus 0 dot x1, which is 0 plus 0. So the function is 0. As you can see, this is a linear function. Or the function can be 0 dot x0 plus 0 dot x1. So in this case, the function is going to be x1, or in this case, it is going to be x0 or x0 plus x1. Okay. So let me call this function L0 of x, L1 of x, L2 of x. I hope you can see what I'm doing here, and let me call this L3 of x. Like essentially, I'm taking the integer value of these strings and I'm making them the indices of the linear function. Okay. If you have any doubts, again, feel free to ask. So I should have duplicated it before. No problems. Take this, select all of this, and get rid of it. The rest. Oh, oops, sorry. Yeah. Yes. Can you hear me now? Can you please confirm? Yes, thank you. Reason, my internet connection failed me. Today seems to be a very bad day for all of this. So yeah, out. Okay, chat and everything is still alive. So was everyone with me until this slide? Can you please confirm where I defined these Boolean functions? Thank you. So now what we are going to do is we are going to write the truth tables of these functions. I apologize for the interruption. Okay. So sadly, I don't generate my own network connection. Yes. And yeah. So let us just construct this table. So in this case, the function is just the zero function. So I know the function has value 0 for all possible inputs. In this case, I know f of x is, let us go back and look. It was x1, not x0. So x1 is varying as 0, 1, 0, 1. So in this case, the output is going to be 0, 1, 0, 1. L2 of x was x0. So that is 0, 0, 1, 1. And L3 is the sum of these two. So the sum of these two first is going to be 0 plus 0, that is 0. Second case, 0 plus 1, that is 1. Third case, 1 plus 0, which is 1. And finally, 1 plus 1, which is 0. Okay, so please repeat the s dot x expansion. So over here, so any two vectors, if I have this coordinates, s1 to sn, x1 to xn, then s dot x is defined as s1 x1 plus s2 x2 plus s3 x3 all the way till sn xn, where the multiplication between these coordinates and their addition is defined based on the field where the vector space is, like field over which the vector space is defined. So in this case, we are considering the vector, the field of binary numbers or GF2. So over there, addition is XOR and multiplication is AND. So when I'm performing the dot product s dot x between two vectors, two binary vectors, what I need to do is I will take the first coordinate of each, compute the AND of them. I'll take the second coordinate of each, compute the AND of them. So all the way I will go to the nth coordinate and then I will XOR all these values. I hope that answers your question, Apurv K. Okay. So, and that is what I'm free to, work it out on your own and find out. Now leave L0 of x out because that is the trivial case. What am I doing? I'm just multiplying both the vectors by 0 and turning the whole thing 0. So let us ignore this for a second. I mean, look at the other three Boolean functions. What can we tell about them? So L1 to L3 have the following properties. What is the first property? First property is, I really would have liked to have some back and forth here. Doesn't matter. You can readily observe this and see that L1, L2, L3, they all have the same number of zeros and ones. No difference between classical computation and quantum computing. We'll see towards the end. And that's more of a statement and not a question. So I will comment on it later. In multiplication, yes and no. Again, Murali, I will talk about this later. Yes, so they have the same number of zeros and ones. Zeros and ones. Okay. And what other properties do we see? Like what other properties? Sorry about that. So wait, is my voice echoing? Oh, there is
No,
echo on your
no,
side.
no,
Okay, okay.
no. Your
Fine,
voice
fine,
is
fine.
clear. Please go ahead.
No, I got a comment, so I had to make sure. Okay, and second is you will actually see there are some patterns. Like you will see that the truth table also has some patterns to it. Table has some patterns. What are these patterns? That is where like the Bernstein-Vazirani algorithm starts capitalizing on things. So how do we study patterns in sequences of numbers? Like essentially I have the sequence of these four numbers. Okay. So materials and notes related to this topic, please go and refer to Nielsen Chuang. It has an amazing discussion for everything that I'm doing here. In fact, it goes deeper. It talks about general linear systems and how to define quantum circuits and algorithms for them. So it is, a very good source. Again, as I mentioned before, it is a bit of a tough read, but if you push through it, like it took me years to like understand good chunks of it, and there are parts of that book I've still not read. So I'll be very honest about that. So, but nonetheless, whatever I've read, I've greatly benefited from it. So please go ahead and read that. So when we are talking about pattern recognition and stuff like that, there is one standard technique discovered some, 200 years ago, almost. We are like nearing the 200th anniversary of the Fourier series and Fourier transform. Uh, that is the only technique. Even in this day and age, even with all your machine learning and uh, all the other techniques, ultimately, if you want to study patterns, some way or the other, you are going to do Fourier transforms. So, what is Fourier transform? So this is how I'd like to introduce the Fourier transform. Let there be a sequence of two numbers. Now these numbers can be any numbers. Okay, I'm not saying that they have to be bits. These can be any numbers. Okay, so not only bits. So I have two entries, A0, A1. This is my sequence. So my sequence S, okay, so I've already used S before. So let me say I have a sequence, I've used L, I've used S. What is a good letter for this? Yeah, you know what I will say? This is a sequence P. Yeah, I'll call it P. So P is defined as a sequence of two numbers, any two numbers. Oh, the notes that I'm presenting here, like you'll get it when I share it, just like last week. So I have A0 and A1. Now, in a sequence of just two numbers, several things can happen. Now, what are the things that can happen? I can have A0 equal to A1, or I can have A0 greater than A1, or I can have A0 less than A1, or I can even have A0 equal to minus A1. These are some, common relations these two numbers in this sequence can have, regardless of their value. Now, how do I characterize these? So for a sequence of two elements, what I will do is the following. I will calculate two quantities. I will calculate a quantity A, or let me call this, I should not call it A. Let me call this quantity A hat. And let me say this is A hat of 0. Let me calculate this as A0 plus A1. And then let me calculate A hat of 1, which is equal to A0 minus A1. Okay. I'm calculating these two values given a sequence. All right. So now what will happen for each of these cases? What is A0 plus A1? So we can quickly, intuitively understand that A hat of 0 is average, or it is proportional to the average. It's twice the average in this case. So this is the average value of the sequence. And A1 is the difference. So now consider these four values. I don't need the values of the sequence. I don't need to know what the sequence is. If A0 is equal to A1, I can automatically say A hat of 1 is equal to 0. Because whatever these values may be, if I subtract them, they will give me 0. If A0 greater than A1, then A hat of 1 is positive. If A0 is less than A1, then A hat of 1 will be negative. If A0 is equal to minus A1, A hat of 0 will be 0. Essentially, the first term will become 0. So, by performing these random operations on these, two numbers, I'm getting some other numbers which gives me some idea of the properties of the sequence, generic properties that, I'm not particularly concerned with the specific values, but so if A0 is equal to A1, this is a constant sequence. If A0 is equal to minus A1, that is what's called an alternating sequence, where I have a plus value and a minus value, essentially like, your AC and DC currents, where I have a constant voltage or a current and I have a varying voltage and current, where it goes from a positive maximum to a minimum, to the negative of that. So this is an alternating sequence. If A0 greater than A1, it is a decreasing sequence. If A0 greater than A1, it is an increasing sequence. So I can tell all of these things without particularly investigating every single sequence. I just say perform these two operations, give me these two numbers. Based on these two numbers, I can make all these qualitative decisions about the sequence. Now, how is this Fourier transform? You can ask me. So, you know what? I'll just make a new slide and keep it blank. Otherwise, I need to spend too much time erasing things. So, now let me say I'm writing this as a vector. Let me say I'm writing my sequence as a column vector like this, A0, A1. Now, how do I get A hat 0 and A hat 1? I've already told you that A hat 0 and A hat 1 are A0 plus A1 and A0 minus A1. So let me construct a vector P hat, which is A hat 0 and A hat 1. Now, how do I connect these two vectors? The way to connect them is there is some matrix, let me call this M, which when multiplied to A0 and A1 will give me A0 hat and A1 hat. Now, what is this matrix? The first, I need the sum of those two. So I will have 1, 1. And for the second, I will have 1 minus 1. Now, are we familiar with this matrix? Do we know this matrix M? Yeah, sorry, there is no voice, but can I get something in the chat? Are we familiar with this matrix M? So this implies, yes, thank you. So M dot P is equal to P hat. No, this is not an eigenvalue system because this vector is different. So M is actually the Hadamard matrix. So this is what your Hadamard matrix does. Your Hadamard matrix is essentially calculating the average and the difference of the numbers that you present. And based on what the initial values were, you will get an output that will tell you the exact details that you need to know about the initial values. And this is scale independent. Again, these numbers is by original A0 and A1. Yes, so the square root of 1 by root 2, why do we take that? That is to make the thing unitary. Because right now, if I do m dagger times m, I will get a value of 2. So I need to normalize that. So I will give 1 square root of 2 here and another 1 by square root of root 2 there. Okay. And yeah, technically I can define this quantity here as A0 by A1. I can also do this by root 2. But none of these will, remember, these conditions will always be the same. Even if I do 1 by root 2, I will get the same, answers. These, oh God. Okay. This is extremely problematic. Now I have a power outage. Let me see if I can get some light in. Nope, not working. You know what? I'll turn off my camera for this bit because this looks rather intimidating. Uh, yeah, today just doesn't seem to be biting. So,
It's
are
okay.
you able to?
We can hear your voice.
Yeah, you can hear me, right? Are you able to see my screen?
Yes.
You are. Well, uh, the bad news is I can't see my screen because the display just turned off. So let me switch over to my laptop entirely. So that way I should be able to see everything. So I will stop my, yeah, I will share something else and I shall share the PowerPoint. Oh God, no, the UPS will keep beeping. Okay, this is all extremely annoying. Yeah, so let me, okay. Yes, all right. Yeah, so we are back again. And since I have unplugged that, yes, this thing works here. Wonderful. Now, can I zoom into the slide a bit more? Yes. Yeah, I'm sorry. The scale might have changed a bit. Kindly, bear with me because nothing much I can do here. I'm literally in the dark. So yes, so people were asking about creation annihilation operators. Not quite, because your creation and annihilation operators are not unitary. So, that is all I will say. Please confirm.
Yes, yes, yes. Jotishwaran, please go ahead.
Yeah, I'm audible, right? Yeah. No,
Yes.
because suddenly my system was warning me that I have a network issue. Well, I'm happy that things are still running. So, yeah, what was I saying? Yes. So if I have the Hadamard matrices, these are actually these have greater applications in fields like combinatorics and things like that. So this matrix was not introduced for quantum computing. It is just a coincidence that these matrices can be made unitary. Therefore, they can be turned into gates. And because of that, we get, like, in fact, Hadamard matrices are essential for leveraging quantum parallelism. So this is all just, some wonderful coincidence of nature where all of these things align and we are able to use them. Now, why all of this happens, that is a fundamental mystery of the universe, which may or may not ever get answered. Okay, so this is for n equal to 2. Now, what if I have a sequence which is more, bigger than this? Now, let me quickly, create a sequence. Let me say I have a sequence Q that is A0, A1, A2. I have a sequence of length 3. So now, how do I characterize this sequence? Again, I can have many characteristic properties for this. For sequence of length 2, we arrived at, these 4 cases. There can be more cases, but I'm not talking about that. Now, if I have a length of sequence 3, what do we do there? Well, since today we are not talking about Fourier transforms, I'm not going into the details. I will just say this. For a sequence of length n, length capital N, we can create, so essentially these two vectors, 1, 1 and 1 minus 1, these vectors are what are known as the, yeah, so let me try opening the chat from somewhere. Do I have, okay, why am I unable to see? Yeah, so somebody had asked me for, some brief, like
Should
materials
I
for
read?
understanding. Yeah, if you
Should
can,
I?
please, I would appreciate
Yeah.
that. Yes, because right now I
Uh,
don't have my dual display.
yeah.
Yes.
Please provide brief and compact materials and notes from your site so that we can access by the link. Yeah, this will
Oh,
be shared, Vinod. You don't have
yeah,
to worry.
everything
You
that
can
I'm
follow
doing
our
in today's
GitHub.
session will all be shared. For general stuff, oh yeah, this is also something I was meaning to convey to all of you. Santosh ji, if you think it is possible, you can also share them the links of the previous courses that CDAC has conducted.
Yeah, definitely. That I'll do.
You can share the GitHub repos or the video playlists for that. That way
Yes.
they can go there and we will have a more detailed discussion of all these things over there, and they will also have access to Professor Gangopadhyay and Professor Vishwen's lectures where they talk about the physics and things like that and the mathematical side of things. So that should
Right.
help as a very good primer. Over the years, like we've been doing this for 5 years now, many people have said that it is good. So I welcome all of you to like go through the same. Okay, so if I have a sequence of length n, then what we can do is we can create a Fourier basis. Okay, so we can create a Fourier basis. So what is a Fourier basis? A Fourier basis is nothing but, why am I unable to close? Yes, get out. My God. Okay, something very, just 1 second. Okay. Yeah, something seems to have gone wrong with my thing. So let me quickly just save this. You know, once again, I apologize to all of you for these technical difficulties. And let me reshare again. And let me reopen the slides. Yes, and we were here. Good. So yes, I hope the screen is visible now. The slides are visible, right? Hello. Okay, yeah, yeah. Thank you, thank you. Okay, there was again some kind of a network latency on my side. Thanks for the confirmation. So Fourier bases are these vectors. Again, coincidentally, this is also a linear system. So the Fourier transform is also a linear transformation. If I get a sequence, I can apply a linear transformation to it and learn something about the sequence. Okay, that is the takeaway for this. So we can create a Fourier basis. Fourier basis using the roots of x to the power n minus 1 is equal to 0. I will take this equation, I will find the roots of this equation, and those roots will allow me to create the Fourier basis for a sequence of length n. So for a sequence of length 3, I will calculate x cube minus 1 is equal to 0. So this will give me the roots of unity, the cube roots of unity, which are 1 omega and omega squared. So from this, I will just quickly say that I can define the matrix where my first entry is all ones, then I have 1 omega omega square, and my third entry is, everything multiplied by omega. So it is going to be uh, uh, omega omega squared and 1. So that is how we kind of define these operations. Okay. So this is Fourier transform, and with Santoshji, can you please read the last question? That seemed relevant. Hello. You know what? I will open the chat window separately so that I can read those things. Yeah. No. About? Yes, let me reshare the slides again. Yes, good. So yes, so the idea is to use all inputs and find the value of the function, which will be our sequence, and analyze exactly. Yes, Dibyajyoti Sahu, you've got the gist of it. So that is where we are going towards. So now, what if n is 2 to the power some small n? Capital N is 2 to the power some small n. If I have a sequence of this kind, once again, I can create. So for the special value of n, I can actually do something different. Essentially, what I can do is the following. I can actually do this. I can do the two variable, because what is happening when I have a sequence of length 2 to the power n? When I have a sequence that is of length 2 to the power n, it actually, I can break this into distinct sets of 2, and I can do the same for like n steps. Like essentially, I can create a binary tree out of the sequence. Now you can ask, how do I do this? So remember, for a sequence of length 2, what did we do? I considered I considered this A0 plus A1 and A0 minus A1. So what I'm going to do is this. So let us take a case where n is equal to 4. I have my sequence that is A0, A1, A2, and A3. Okay, this is my sequence. Now, first, what I'm going to do is I'm going to take this pairwise. Okay, and I'm going to do the Fourier transform for these two subsequences. So from this, I will get A0 hat, A1 hat. Let me say A2 plus, let me write A2 plus A3 is equal to A2 hat, and A2 minus A3 is A3 hat. Okay, I will have these two values. And then what I will do is, instead of grouping the sequence like this, I will group the sequence in terms of these values. So I will try to calculate the average of averages. Essentially, this is one average, this is a second average. So I will calculate the average of A0 and A2 and A1 and A3. So that will give me the next set of values. And then finally, I can treat the entire sequence as one and get the overall average of it. So now how do we perform this? Like how do we get the essentially linear transform? What is the Fourier basis for it? So the Fourier basis will look something like this. So let me again pop up a new slide. Set the layout to blank. Yes. So essentially what I'm saying is, so I have a 4x4 matrix now. Okay. And I'm multiplying this with my A0, A1, A2, A3. Okay. Now this is a sequence of length 4. Like standard Fourier transform is, I will take x to the power 4 minus 1 is equal to 0, get the 4 roots of unity, which in this case are 1, I, minus 1 and minus I. And then, I will get the Fourier basis and I will do the discrete Fourier transform. There are fast algorithms for doing it. I will do FFT and I will get the Fourier transform. But an alternate way of doing the same Fourier transform is first calculate the average of all 4 values. So I do 1, 1, 1, 1. So that will give me the total average of the sequence. Then what I will do is I will calculate the differences for these two, like pairwise. So I will do 1 minus 1, 1 minus 1. So this will give me the differences and the sum of the differences. So essentially this is going to tell me the average pairwise difference for this entire sequence. Then what I'm going to do is I'm going to take the difference of the averages. I'm going to do 1, 1 minus 1 minus 1. Essentially, oops, it's fine. I will write the matrix in its entirety later. And finally, I will do 1 minus 1 minus 1 and 1. So what am I calculating here? The first vector is going to be the sum of all 4. The second vector is going to be A0 minus A1 plus A2 minus A3. So let me say, so the first quantity is A0 plus A1 plus A2 plus A3. The second quantity is A0 minus A1 plus A2 minus A3. The third quantity is, third value I will get is A0 plus A1 minus A2 minus A3. And the fourth is A0 minus A1. And this, I can write it as minus of A2 minus A3. The entire whole minus. Okay, there is a bracket here. So what am I doing here? I'm taking the average of averages. I'm taking the average of the differences, then difference of the averages and difference of the differences. So when I have a sequence of length 4, I can define a Fourier basis like this also. And if I look at this matrix, can someone now tell me how I can create this matrix? So before that, a general question is, anybody here familiar with tensor products? Can I get some response? Yes. So look at this matrix. Look at this new matrix. Let me call this M2 or M4. M4 would be a better thing. Yes. So how is M4 related to my previous matrix N? Can you tell me? Can anyone guess? Exactly. Thank you, Divijyoti Sahu, for your answer. So just one second. Let me drag the chat to this side. Yes. So this is equal to, you know what? Yeah, I'm really sorry. Working with a small display, especially when you're writing stuff, becomes extremely difficult. And I set myself up, I was not anticipating any power cuts. So I'm really sorry for the inconvenience, but that is life. Usually you run into situations like this. You can either say, oh no, there is a power cut, I cannot give the session today, or you do whatever you can and try to have some fun. So yeah, yes. So no, God, this is getting increasingly difficult. Yeah. Yes. So no, I want to draw. I don't want to select. Yes. So M4 is M tensor M. So what is a tensor product? Let me quickly write it. Remember, this is 1, 1, sorry, write it bigger so that it's clearer. This is 1, 1, 1 minus 1. Okay, so similarly, this M is also that. So how do I create the tensor product? I do this 1 into this matrix 1, 1, 1 minus 1. Similarly, 1 into 1, 1, 1 minus 1, 1 into 1, 1, 1 minus 1, and minus 1 into 1, 1, 1 minus 1. Now, if you expand this, if you multiply this number and expand all the 4 rows, you will get this. First row is 1, 1, 1, 1, 1 minus 1, 1 minus 1, and then 1, 1 minus 1 minus 1, and then 1 minus 1 minus 1, 1. So these are the 4 rows. So essentially, if my sequence has 4 elements, then I can index them with 2 distinct binary labels and I can get these vectors. Now, let me take the opportunity and go back to the table. And let me ask you to calculate the following quantity. Calculate y is equal to minus 1 to the power L of x. Essentially, calculate this quantity. Okay, so what is going to happen here in this case? I will write the values of y in black. So minus 1 to the power 0 is 1. This 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 is minus 1. This is 1. This is minus 1. This is 1. This is 1. This is minus 1. This is minus 1. 1, minus 1, minus 1, 1. Do you recognize these quantities? Of course you do, because these are the rows and columns, because this matrix is symmetric actually. If I take the transpose of it, sorry, it's not symmetric. Wait, no, it has to be, yeah, it is symmetric. Shit. Yeah, it is symmetric. So this is a symmetric matrix, and the rows and the columns were actually the Boolean functions, the linear 2-bit Boolean functions. That is what I'm using for the rows and columns here. So if I have a sequence of length 2 to the power n, where n is some natural number, then I have an alternate Fourier basis to define my transforms. So this Fourier basis gives me, no, yeah, this Fourier basis. So essentially for, oh, sorry. So for n is equal to 2 to the power n, the new Fourier basis, it has a new name. So this is known as the Walsh Fourier basis, because I think in the early 1950s, this gentleman, I think he was either an electrical engineer or an early computer engineer. So he came up with this transform. So this is called the Walsh Fourier basis. Previously, for different reasons, Hadamard has also defined this, but he did not think of it as a Fourier transform. So the alternate name is the Walsh Hadamard basis. Walsh-Hadamard basis. So this will help me identify which, oh yeah, before that, let me go ahead and quickly, can you try to take the dot product of every row with every other row? Shall we try to take the dot product of the first row with the second row? What will be the answer? Can someone in the chat? Yep. What about the first with the third? It will still be 0. What about the second with the third? It will still be 0. So you can go ahead and try this. You take any row and take the dot product of it with any other row. Yes, they're all not only linearly independent, they're also orthonormal. They're orthogonal in this case. They have not been normalized. They're orthogonal. Essentially, what I'm saying is these vectors form an orthonormal basis. So this is the Walsh Fourier basis. So essentially, this is a orthogonal basis defined by the linear functions of, or rather linear functions over n bits. And this is the secret of your Bernstein-Vazirani algorithm. Because what is my input sequence? My input sequence is always a linear function, which implies my input sequence always corresponds to, oh no, I don't want this slide, I will go earlier. If I'm considering the two variable case, my input sequence is always going to be one of these four. It cannot be anything else because these are the only possible linear functions for two variables. If I had three variables, how many linear functions will I have? Can somebody tell me? If I had three variables, how many linear functions can I define? No, 0 is also counted, 8. I don't like L0 is definitely a linear function. But it is a trivial linear function. It's just, setting, because 0 plus 0 is 0, so setting all zeros is a linear. Yes, I will get 8 linear functions. And the corresponding basis will have 8 orthogonal linearly independent, like of course they're linearly independent, it will have 8 orthogonal vectors. So when I choose a linear function, I'm going to choose only one of them. So when I do the Walsh-Hadamard transform, what will I do? I'm just taking the dot product of these vectors with all the basis elements. So which vector will the dot product be non-zero? Only for the vector corresponding to the function. Every other case, the dot product will be 0. Is that clear? Or should I explain it once again? Because this is essentially the Bernstein-Vazirani algorithm. After this, we are going to the demonstration. And unfortunately, because of the present conditions, the room is getting darker and darker. Okay, let me re-explain. Okay, so putting y or l, we are using y. Yes, we are using y because you see, if my matrix had too many zeros, then implementing it like you'll see why. You'll see why. Just give me a second. Okay, so this is an orthogonal basis. Therefore, if I have a sequence or if there is a sequence P given by minus 1 to the power some Li of x. If I calculate this sequence, so P is minus 1 to the power Li of x. Then if I take the Walsh-Hadamard transform or the Walsh Fourier transform, I will automatically get what the value of I is, because that is the only vector which will give me a non-zero dot product with it, because the basis is orthogonal. Every other linear vector will take the dot product with this and become zero. Only the case where the Lith basis vector is concerned, that will be the only vector which will multiply with this and give me the non-zero value. So then the Walsh Fourier transform will give the value of I. And that is the Bernstein-Vazirani algorithm. So how do I perform the Bernstein-Vazirani algorithm? The quantum circuit, to briefly sketch. First, I will need to calculate the entire sequence. So let me, start from here. So first, I have the oracle of my Boolean function. So I have my oracle, which I call UF. Now, what does UF do? Let me write it here. UF acting on ket x will give me -1 to the power f of x ket x. Okay, I'm defining the oracle like this. So the coefficient of x is going to become, so this is nothing but y of x, right? As we had defined before. So this quantity is y of x. So I have the oracle for UF. Then what do I do? In front of every input, I will put the Hadamard gate. So all the way till n. So I will have the Hadamard gate. Can't we do the dot product with strings of 0, 1, where 1 only appears and get each bit of the secret code? Can't we do dot product with strings of 0, 1, where only 1 appears once? But you need to have enough values of the function. Yes, you can do this, but you cannot do this with only. So this is this is a question from, I hope your name is Agile or Agile, Matthew. So, like how many vectors do you need to have the dot product for this? Like I will need n vectors. But what you're going to see here is I will perform the Hadamard here. So this part, this will generate the sequence. So this is the sequence generation. So this is the sequence generation. Then after this, I need to perform the Walsh transform. Now, what was the Walsh transform? It was just Hadamard tensor, Hadamard tensor, Hadamard tensor n times. How do I do that? I just apply Hadamard to each qubit. That is all. So I do the same thing again. So I apply Hadamard here, all the way till the end. I apply the Hadamard here, and then I observe the result. This result will always be the vector S. Guaranteed, as long as my quantum computer initial qubits are all 0. I should have not forgotten to mention that. Initially, if I start with the all 0 state, and if my oracle is defined like this, if I perform this, then I will get the value of S as the result. So this is the Bernstein-Vazirani algorithm. Okay. So let us look at a demo. I think, unfortunately, no, I can, yes. So for now, please keep looking at my slides. I will log in and, start the demo over here. So yes, now I'm briefly closing the chat. Wait, what? Let me stop sharing and let me share Qniverse window. Yep. Yes, I hope you can see this circuit creator. So
Yes.
first, let me create a linear function. Now, what gates do I need to create a linear function? The answer is I actually only need a cdot gate. And you know what? Let me create a three variable function. So let me change these registers to 4. Okay. Yeah. So uh, can someone give me a value of s? Can someone in the chat give me a 4-bit string? Let us see if we can get that quickly. Just type in a 4-bit string. Yeah. 1010. Brilliant. Two people got the same string, so I'm going to use that. Okay, so 1010 means x. So x0, x1, x2, x3. If I use 1010, I'm doing x0 plus x2. Okay. So, okay, we have done a 4-bit string. So, you know what? Let me raise it to 5. No issues at all because this algorithm is fairly straightforward. Okay, so I take the first one, add it here, and I, no, don't go down. Yes, edit, go all the way down to Q4. Okay, no, oh no. Yeah. Controller is Q0. No, target is Q4. Controller is Q0. Yes. Yeah. And the second one was Q2. So I'm going to set this over at Q2. I'm going to edit this and make it target is Q4, controller is Q2. That is it. This is my linear function. For the string 1010, this is my linear function. I can enter any x and check the output. It is going to be x0 plus x2. Right? So, but how do I create the, like essentially the other form where I get the face value? For that, I do the following. So you know what, before this, I will group, wait, it's supposed to be, yes. I will group these two and let me call it uh, x0, x2, or, oh wait. So how do I write this? Can I do, eh? Let me say this is 1010 is what?
XZX.
Yeah, yes, I can write it like that. I'll just say xx for now. So this is a linear function, not linear function, linear function with s equal to 1010. Huh. This is some gate. Okay, so I have this gate. Now, how do I perform the Walsh-Hadamard transform? First, I need to, oh yeah, first I need to change this into a face oracle version. Like from a bit oracle version, I need to change it to a face oracle version. How do I do that? I will flip this and then I will apply a Hadamard here. So now this has become a face oracle. You know what? I will select this. Wait, I can't. Really? Yes, I should be able to. So let me call this P XX or whatever. And let me say this is face oracle of linear function. So here I have it. Now what do I do? Now this whole thing, if I give an x, it will give me minus 1 to the power f of x. So I apply Hadamard. No. Apply Hadamard to this. Wait. Yes, let me move this over. Apply Hadamard here. Here. Oh, also here and here. So now if I go down and check the probability distribution, let me see if I can zoom in on this. Yes. You can see that all of these have the same probability value, 3.13, 3.13. So the entire table has been created. Okay. In fact, yeah, the entire table has been created. So let me zoom out once again. If I apply the Hadamard's here, I should get only one vector when it comes out. Well, technically I will get two vectors. But yeah, to rectify that, what I'm going to do is I'm going to apply. I should have done that. It doesn't matter. Let me just, do I need the X? No, I don't need I need the X after this. And I apply a Hadamard here. So this way the last qubit will become 0. Okay. Now I should have a vector. My probability distribution should have only one spike. Let us see if that happens. See? Wait, what? It's in all zeros? That's not right. Something is definitely wrong. Why did it go to all zeros? I definitely defined a gate in here. Expand it? Yes. Yeah. You know what? Let me get rid of this and let me use our XZX. Huh? Wait, what? Oh, this is defined only over 3. Why is that? Oh, oh, for some reason, yes, that is why things were not working. You know what? Yeah, the saving was an issue. So let me quickly create the whole circuit over here. So I will add one cdot over here where no, the target bit becomes Q4. Save this. I will bring in another cdot over here. I will move all these guys one step. And I'll move this one to Q2. And I will change the target to Q4. Save it. Yes. Now it should have only one spike. As you can see, it has only one spike. And oops. Yes. Where is that spike? It is at 1, 0, 1, 0. Like the order is always reversed here. So as you can see, by just taking the Hadamard transform, I'm able to find out the value of S. In a noiseless quantum computer, I need to do this, and the moment I perform the measurements, I will get the value of S. Like, you can replace this with any other Boolean function, and you will see that this particular spike that we see will keep moving to different values. Okay, so is that somewhat clear? Are you getting an idea of how this algorithm works? Oh, so S is given like the oracle. Yes, yeah. So now, let me, what is the time? Oh God, okay. Because for the last few minutes, I've been unable to see the clock because the room is completely dark now. Okay, let me stop sharing this. Do I have another 5 minutes, Santoshji?
Yes, Jotishwaran.
Thank you.
Quickly,
Thank you.
not more than 5 minutes.
Yeah. That's all I need.
Yeah.
So let me go back to the slides and let me see. Now this quantum circuit, which is what we created there, is supposed to solve the Bernstein-Vazirani problem in constant time. As you can see, even if the number of qubits increase, I just need to use UF one time. That's it. If I use UF one time, I will get my answer. I will be able to find the value of S. But the question is, where did I get UF from? You gave me the linear function, I constructed the U. Since you gave me the linear function, you already knew S. There was no need to perform this exercise. So the availability of the quantum oracle, where does it come from? And even if I have the quantum oracle, can't I just explore what gates are in there? That way I can find what the linear function is. I can find what S is. Because depending on S, I added my C naught gates. And C naught gates are the only gates required to, C naught or control Z gates are the only gates required to define a linear function. So not control Z gates. Z gates are the only gates required to define a linear function. So where did the quantum Boolean oracle come from? Like, if I have this, do I need to perform this quantum computation to get the value of the function? Or can I just probe the oracle and get the value of the function? The answer is yes, I don't need to perform this algorithm. I can just probe the quantum oracle that I have to get the value of the function. And you can think, I'm cheating, but no. In the present day, if I have a classical circuit that is, a cipher or some crypto system, or, it is some memory architecture, there are attacks where people do exactly this. They don't bother with the input output. They just go to the circuit, see what calculation it does. They make a table of all the values that the individual registers are calculating, and from that they guess what secret value is stored in there. These are called hardware-based attacks. These exist. All existing classical ciphers and upcoming post-quantum ciphers are all susceptible to hardware attacks. So they don't even play by these mathematical rules. Like, one doesn't even need to wait until Shor's algorithm to break RSA. Well, Shor's algorithm can be broken using classical methods too. But if I have something like AES 256, there are proper hardware attacks where people literally just look into the circuit, see what is there, and break the cipher. They find out what the secret key is. So if I use the same logic, if that is true for classical systems, that also has to be true for quantum systems. Then why am I even performing this quantum algorithm? And that is the main problem with this Bernstein-Vazirani algorithm. Like, yes, it gives a problem. It definitely shows speed up. So I told you that there is a decision version of the problem, but unfortunately, due to today's situation, with my network issues and all of these things got dramatically slowed down. I apologize for it. If we ever meet again, I will, try to discuss the decision variant of the Bernstein-Vazirani problem. Over there, we will show that, yes, I will go back to the slide and just, impress upon the line. So, no, yeah, this. So there is a super polynomial speedup. But over here, what should be noted is both algorithms. Both algos, classical and quantum, are not in P. And that is the problem. Yes, the quantum algorithm has a super polynomial speedup than the classical algorithm, but both of them have exponential time complexity. Like, the classical has super exponential, but the quantum algorithm also has an exponential time complexity. So yes, it is faster than the classical algorithm, but it doesn't make it efficient. It doesn't bring it into P. It is still in the NP class. And whether it is in NP, it is not proven. Whether there is a polynomial time algorithm, we don't know. So while like Bernstein and Vazirani's ultimate form of the algorithm does give us a speed up, it actually does not make things significantly simpler. I will still need to use an exponentially large amount of resources on a quantum computer to solve the problem. If I need to use exponentially large amount of resources on a quantum computer to solve the problem, I can do the same on a classical computer and solve the same problem. So yes, while Bernstein-Vazirani gives me these mathematical advantages, the practical advantages are actually very limited, which is why usually Bernstein-Vazirani algorithm people discuss in the academic context. Nobody talks about it in the practical context. But to understand how quantum speedup works, this is one of the best algorithms. Like, as I've shown you, the logic is essentially Fourier transforms. These have patterns. The patterns, with using the patterns, I can generate orthogonal vectors. Since all these vectors are orthogonal, if I know I have only one of these vectors, I can just take the dot product with all of them and find out what the value of S is. And that is what we are doing in the Bernstein-Vazirani algorithm. So yeah, with that, I will end my session for the day. I will take any questions that are there for a couple of minutes and then we will call it a day. Yeah, one general question. Oh yeah, so you know what? This time around, I will try to be a bit more non-dismissive. How, okay, how to construct a circuit for any model or problem? So ultimately, you need to construct the classical circuit that you need and then turn it into a quantum version. That is the only known process. So these days, people are doing it blindly. They're taking the classical circuit, they're converting it because we have very powerful quantum, classical computers. It can do that very fast. And right now, our quantum computers are so weak that if the models become slightly large, I'm not even saying too large, they will, like these sizes can still be dealt with classically, but on a quantum computer, I still cannot run them. So in that case, like the quantum version of the algorithm will not run, but later on, as things become bigger and bigger, if I want to run a quantum machine learning algorithm on a general purpose quantum computer, then how do I generate the circuit? That is one of the biggest open problems in quantum computing. In fact, that is a problem that might, if I don't know, again, like we'll have to see this in the future, depending on how things play out, that might make the overall enterprise of generalized quantum computing impractical. Because to create these oracles, to create these circuits, the same problem we encountered in the case of Shor's algorithm. Like, yes, I can do a to the power x mod n, but how do I create the circuit for that? I don't know. It takes time. So, yeah, a whole bunch of thank yous. How to start reading the book by Nielsen and Chuang? I mean, should you start from the very first chapter? Read the introduction. Nielsen and Chuang give an idea as to how to read, depending on your, like background level and, things like that. So they give that mathematicians should read in a particular order, physicists should read in a particular order, engineers should read in a particular order. So that is like a very well written book. So just read the introduction of the book, try to understand it, and that should kind of give you things. Is there a real-time application of this version of the algorithm? Yes, there is, but as you can see, this algorithm that I showed is a linear problem. Like these are, very well solvable using classical means. Like linear programming is a very old discipline. I think linear programming is almost as old as Isaac Newton. So, since then people have had efficient ways to solve linear problems. So any application that I can develop for the Bernstein-Vazirani algorithm is readily solvable on a classical system. Yeah, all right. There seem to be no more questions.
Yeah, thank you, Jotishwaran. Today also it was an exhaustive session,
Yeah,
and you
and
have
I once
taken
again,
a.
like, I know I'm not to blame for all of this, but, I'm sorry that things on my end were not optimal. But
That's
I
fine.
hope
We can
people enjoyed the
understand.
session.
Yes, that we can understand. That's fine. And you have taken up all your time to answer the questions of the participants with so much patience. And thank you for that. And we hope we will connect with you in future
Yes.
series
So
also.
the name of the reference book and stuff, it's in my slides. So when I share my slides, you will get the names. Okay, do not worry. Yeah. So
Yes.
yes.
With this note, thank you, Jyotishwaran, for accepting our invitation and presenting the two algorithm shorts and Bernstein-Vazirani. Next week, we will see another quantum algorithm called Simon's algorithm. With that note, thank you all the participants. Hope to join with you next week. Thank you all.